Alright, so today I'm going to be explaining this important paper with the title Deep Hierarchical Graph Alignment Kernels. This paper in HK 2024. Typical R-convolution graph kernels invoke the kernel functions that decompose graphs into non-isomorphic substructures and compare them. However, overlooking implicit similarities and topological position information between those substructures limits their performances. In this paper, we introduce deep hierarchical graph alignment kernel to resolve this problem. Specifically, the relational substructures are hierarchically aligned to cluster distributions in their deep embedding space. The substructures belonging to the same cluster are assigned the same feature map in their reproducing kernel Hilbert space, where graph feature maps are derived by kernel mid embedding. Here you see the structure of, for example, aspirin, the structure of 2D depictions of aspirin and other molecules. The computation of substructure similarities is strict. For example, all non-isomorphic substructures are treated as the dissimilar ones, which impedes the precise comparison of graphs. In addition, the R-convolution graph kernels neglect the topological position information between substructures, which plays a crucial role in the characteristics of the whole graph. For example, whether or not a drug molecule is effective on a disease. So we propose a new graph kernel called Deep Hierarchical Graph Alignment Kernel. Specifically, we define a new graph substructure named B with edge hop slice around the node to capture the structural information. Then we embed each slice into a deep vector space by natural language models. Here, the framework of DHGAK is presented with slice width B is equal to 1 and maximum hop is 1. First, we construct the hierarchical B with edge hop slice for each node in G1 and G2. Then the encoding of the slice is embedded into deep embedding space via natural language model and update by equation 1. Given an undirected graph, we build a truncated breadth-first search tree. Then with that, we can define the B width of edge hop slice. So for each node, we can do it. So for example, here shows B width edge hop slice of node V1, where B is fixed as 0 and edge ranges from 0 to 2. This is the definition of deep slice embedding. So because given a label embedding function, which is learned by NLM, a G is a label embedding. D is the dimension of the embedding. The embedding of a B width edge hop of node V can be defined like this. The deep alignment kernel quantifies the likelihood of assigning 2 points to the same cluster across all clustering methods. Finally, our deep hierarchical graph alignment kernel is defined like this. So they did experiments on these datasets like protein, enzyme, all of these classification datasets. and they compared different models. Here you see comparison of average classification accuracy. DHW BERT applying Wasserstein distance instead of DAK fails to complete in 24 hours on large datasets. So it takes more than 24 hours if you want to use DHW BERT on CoLab dataset.